Okay. So when I put together my slides, lecture slides, I call them lecture 1, 2, 3, and 4, right? So right now this is lecture 2. But in lecture 1, we talked about like general concepts of optimization from the modeling perspectives, the applications, the history of optimization, the role of optimization versus ML, like what optimization can do that ML cannot do, these kind of discussions. And at the end of lecture 1, we briefly talked about what I mean by optimization under uncertainty, right? What kind of, what sources of uncertainty are there when you talk about different types of problems trying to solve. Right, so we're gonna delve more into this topic. And as I mentioned, things will become slightly, slowly, but hopefully nicely, mathier and mathier. But I'll try to keep all of us on the same page as much as possible. That's the plan. So let's talk about types of uncertainty. Okay, we talked about sources of uncertainty, but when you talked about all different types of uncertainty in different problems, what I really mean by uncertainty is, well, some of the parameters in your optimization are uncertain, right? The time that I take to save this patient, well, it is maybe on average supposed to be 15 minutes, but could be as short as 10 minutes, as long as 20 minutes. Well, that parameter, right, the minutes, is gonna be in my optimization problem that'll affect my optimal solution or someone's optimal solution, right? What if that is uncertain? How do we do this? Okay, so parameters are uncertain, but oftentimes distributions may be available, right? The time that I just mentioned, I described it as almost kind of uniform distribution from like 5 minutes to 20 minutes, where whatever is in the middle is probably the average. That's the distribution. So you can assume some distributions. If there are multiple parameters that are uncertain, you can build individual distributions for each of the parameters, or you can even establish a joint distribution that covers all of them. Often cases, it suffices to know only the mean and variance of the parameters, in which case you'll be using some moment-based approaches. There are different approaches to uncertain parameters. Your parameters can be uncertain exogenously or endogenously. Okay, exogenous uncertainty, it means your parameter is uncertain because of some external factors that are out of your control. For example, the first case here, consider a farmer who must decide on the amounts of various crops to plant. The yields of the crops vary depending on the weather. Okay, weather is something that you cannot control, that you cannot have control of, right? So that's an exogenous uncertainty that affect your performance. You have to be cautious. Endogenous, well, consider a surgeon who must decide on the surgery order and timing of a certain number of patients awaiting transplantation, right? 장기이식. The order and timing for each patient affects the survival probability distributions of other patients. If I want to treat a very specific patient and put him or her my number 1, then all the remaining 9 patients' survival probability will change because of my decision, right? Endogenous uncertainty. Okay, so high-level modeling idea. We're gonna be thinking about some modeling components. The first one, of course, is data. I'm gonna be using psi, right? For parameters that are supposed to be uncertain. What we can do is we can collect data, right? We're gonna be collecting n parameters from data, which means we can treat them as my empirical data. Okay, n of them. Okay, they could be demands, they could be returns, they could be any parameters that are uncertain. I'm gonna denote the random variable for this by psi, the same psi, but with no subscript or superscript. Okay, I normally use like capital letters for random variable, but oh well. Okay, so what that means is there's gonna be some outcome from some sample space right? And the nature rolls a die, and there's going to be some outcome that I observe, and depending on that outcome, there's going to be some parameters dictated by that outcome. Okay, so what I can write is basically something like this, right? Psi of omega is going to be a vector that basically encompasses like all the parameters that are supposed to be uncertain. Okay, and it's going to be just arbitrarily in arbitrary dimension like d. So a decision x is constrained in big X. So whenever you see big X with no subscript or superscript, that's a feasible region for my decision X. And my objective function is to minimize f of x given psi. Okay? Almost always we're going to be assuming minimization unless otherwise mentioned. Okay? Then what do we do? Well, we solve the problems like this, right? So we minimize or we find an x that minimizes the expectation or the expected value of x over the uncertain parameters, right? And psi, probably it follows some kind of distributions, maybe, right? So z star is going to be the optimal value of this problem, right? Parameterized by psi. X star is going to be the optimal solution to this problem. So whenever you see z star is the optimal value, x star is an optimal solution. Does that make sense? Okay. And whenever you see psi, that's a random variable. Okay. Given some distributions of psi or distribution of psi, we can optimize over sample min. That's one of the immediate reactions that you can take for this kind of modeling, right? So what that means is you just take all these data points, and instead of solving this true problem because you don't know exact distributions of psi, you can approximately solving it by sample average approximation. What that means is, well, you take the average of the objective values where each objective value is going to be dictated, like governed by that empirical data point x or psi I. Okay, you take the sum, you take the average, and it's going to be x hat superscript SAA, sample average approximation. So whenever you see x hat, almost always I try to mean some approximate solution. Okay? That's a sample average approximation. It could be computationally very tediously burdensome because, well, there are many, the sample size could be too large. So instead, what we can do is just to discretize the data into multiple scenarios and minimize over them with the probabilities that are associated with such scenarios. So what that means is each scenario will lead to the same psi value. Okay? And some psi is going to be more likely to happen than other psi's. Like if you think about the observed scenarios, that psi will be assigned higher not distribution, higher probability that will be taken into account when you try to compute the expectation. Something like this. Okay? Not too bad, right? Okay, so the general approaches when we think about how to deal with this kind of situation. Now, I'd like to talk about a very specific setting. And this setting is for me to really talk about how stochastic programming works. Right? Okay, okay, it's better. Okay, like you to think about this problem, minimize C transpose X plus Q transpose Y, where X and Y, both of them are variables. There are constraints, right? The first constraint is the typical one. The second constraint looks weird in the sense that, well, it has both X and Y, and X, the constraint matrix T, Y, the constraint matrix W, and the right-hand sides are B and H, right? A very specific setting for this problem is that, well, the reason why I distinguish between X and Y is because I want to treat X as my first stage decision. Okay, Y is going to be my second stage decision. X I'll have to determine now, today. Y is what? Is something that I can determine maybe next week or at the end of like this year, right? This time of the year, especially the beginning of the year, so you make a decision X, and something will happen in the middle, right? That'll affect the expected performance of X. Then I'll have to do something to make up for it by making a follow-up decision Y. Okay? So Y, in that sense, is also called a recourse action or recourse decision. Okay? So here's the trajectory of my decision making. Basically, X. Okay? X is the decision that I have to make right now, and we call it here and now decision. Here and now decision, what that means is once I make decision right now, which is my X, I cannot undo it. I cannot change it. That's done. I'll have to live with it. And then some uncertainty is going to be realized. Realized. And based on that uncertainty or scenario realized, I'll have to take a recourse action. So this is how it works. Does that make sense? So two-stage decision making. I mean, what we're going to do is what is called two-stage stochastic programming. Okay? So think about the farmer's problem that I just mentioned, right? The beginning of the year, the farmer has to determine how much crops to plant, be it like beans, corns, and wheat. He has to determine the portions of his lands, right? Committed to a specific type of crops. And the weather scenario is going to be realized. And it could be really bad weather, then he'll have to do something. It could be really good weather, then he can do something, right? Okay, some assumptions that I'm going to be making for some basic understanding of stochastic programming. Data is supposed to coming from very specific distributions, and you assume these are known. And uncertainty is going to be exogenous, like the farmer's problem. Some decisions are made before realization of uncertainty, some are made after, and it's going to be the recourse actions. Okay, so I said one of the easiest ways of modeling uncertainty is a scenario-based approach. So take that farmer's example. He can categorize what can happen to his parameters, let's say, in different types of weathers, right? But we want to keep his model reasonable in the sense that there's only so many different types of weathers that it can count, be it like as simple as hot, moderate, and cold weathers. And depending on these weathers, his yield rates will be determined, right? There will be three different factors for uncertain parameters, something like this, right? Your investment decision, the market situation is going to be uncertain. You can categorize them as like up, down, or good market or bad market. Okay? Now, again, we're going to let psi of omega denote a random variable consisting of all random parameters. And what that means is my psi of omega is really, whatever that is uncertain. Right? In this case, let's say the objective function coefficients for the y decision variable is uncertain. T is uncertain, which is the constraint matrix for x in the second decision, second constraint. And let's say H is uncertain, which is the right-hand side of this. So I'm looking at this guy, this guy, and this guy. Okay? And the expectation in the objective function is taken over psi, of course. So what that means is if you enumerate all the possible objective functions in the second term, depending on these scenarios, right? Each term of it is going to be multiplied by the corresponding probability for the specific scenario. Does that make sense? Okay. So this part is not subject to uncertainty. So nothing's changing here. It is only the second part of the objective function that is subject to uncertainty. So I have to take the expectation term. Okay. The T, not that the name is important, but the T matrix called the technology matrix that connects Y and X, right? As soon as you determine X, right, it's going to be multiplied by T, and that will change the feasible region for Y. You can almost think of it as this. You just move it over to this, and then, oops, this thing will be a new right-hand side for your Y decisions or the Y constraint. Okay? All right. Just to make sure that I'm not missing anything. Okay. And W, we assume that it's non-stochastic so that we have a fixed recourse. As soon as certain scenarios realize, we immediately know what the recourse has to be. That's the assumption. That's one of the parts that makes our algorithms effective. Any questions? Yeah. Yeah, it is just for classification purpose, right? Omega, you can purely think of them as kind of some kind of outcomes from your experiment. And depending on what omega shows up, you can kind of set your parameter values like psi, right? Okay. So you can also just write them as like Q of psi instead of Q of omega, and nothing changes really. Just for rigor. Okay, so this is how you formulate this problem, right? Two-stage stochastic program. Does that make sense? So how does it really work in real life, like modeling? Does it make sense, like conceptually, like abstract manner? So I'd like you to think about a very simple, not very simple, but not too bad, not too crazy example that I use in my class. Just the following. Okay. Is it too small? Is it too large? Okay, let's think about this question. The school plans to contribute to 3 large-scale international research projects. Each project will run on 3 external servers like A, B, and C. Servers are server A, server B, and server C. Each server has a different operating cost and provides a different level of productivity for each project. The school wants to determine first how many hours to purchase for each server. Server A, how many hours? Server B, how many hours, right? And also how many tasks to complete for each project. Let's say there are 3 projects, project 1, project 2, project 3, okay? Completing one task for a project needs a specific combination of 3 servers, okay? For example, one task for project 1 requires 8 hours of server A, 4 hours of server B, and 2 hours of server C. So that is actually written in this table. One task of project A requires 8 hours of server A, 4 hours of server B, and 3 hours of server C. And similarly, one task of project 2 will require 3 hours of A, 2 hours of B, and et cetera, et cetera. And the assumption is that the server hours cannot be shared for different projects. Okay? If 8 hours is contributed to project A, that 8 hours is only for project A. They cannot be redundantly used for project 2 or project 3. That is the assumption. And also, the server hour costs us, right? Per hour cost for server A is going to be $200, $400 for server B, and $520 for 1 hour of usage of server A. Server C, I'm sorry. Okay, C. Do you understand the question? Does that make sense? Okay, so that's the story. So using this information, you can connect like the decisions for how many hours to purchase for each server, and also how many tasks you can complete. Okay? For each project, the government actually limits the number of tasks that the school can take on. And it's going to be shown in this table, right? Project A, well, it gives me $6,000 of revenue per task. So if I were to be very greedy, I'm going to be just all in for project one, but the government puts a limit so that I can only take up to 150 tasks for project one and 110 for project two and 225 for project three. Does that make sense? Okay. And finally, the number of tasks completed is converted to the revenue. So one task of project one is $6,000, $4,000 for one task of project two, and $1,000 for project three. Okay, so can you write an optimization model so that we maximize the school's profit by, well, determining the number of hours for each server and the number of tasks to complete for each project? What do you think? Do you want to give it a try? Maybe. Not sure if I can catch. Well, you can formulate this part first, I guess. What would be the constraints for this table or these numbers? Right, the server or project requirement of server hours. Well, I would say the very first step that you have to do whenever faced with this kind of problem, when it comes to modeling, you'll have to determine your decision variables. But conveniently, decision variables are given. You just need to define notations, right? So I'm gonna do is I'm gonna define XA, XB, and XC as the number of tasks to complete. Oops, number of hours to purchase for the three different servers. Okay. I'm gonna also define Y1, Y2, and Y3 to be the number of tasks to complete for projects. Okay. Then using these numbers, what I can do is I can define my Y1 as a function of what? Well, XA, right? No, Y1, I'm sorry. I'm confusing myself here, right? As a function of your axis, okay? So what kind of constraints can you write here? So I'm gonna just write everything here. So this is what I do. Okay, Y3 will become my XA, right? Because Y1 is the number of tasks to complete for project one. And for each task to complete for project one, I will need 8 hours of server A. For each task to complete for project two, right? I'm requesting 6 hours of server A. So whatever the number of tasks to complete for project one, two, and three, if you add them up, multiply by the corresponding requested hours of servers, that's gonna be the number of hours to purchase for server A. Does that make sense? Okay, so this is how we do it. And that number is actually, why don't I actually write it here? Right? Let's just make it a bit small like this. And similarly, I can define my XB, XB, XC like this. All you need to do is just look at the rows of these numbers. This is it. And of course, my XA, XB, XC, they're integers. But for now, let's assume that they can actually be continuous, right? That's my assumption. I'm gonna allow my X and Y to be continuous, which means I can buy a fractional number of hours, of course, right? But even like fractional number of tasks to complete for each project. Okay, so this first set of constraints. And also, if you look at the Y's, Y is the number of tasks to complete, or more specifically, number of tasks that I'm allowed to complete because, well, it's going to be limited by the government limits. And these are 150. I'm looking at this, these numbers, right? Oops. 110 and 225. And all my X is non-negative, all my Y's non-negative. That's it. Does that make sense? It's not too bad. And what is my objective function? My objective function is to minimize cost. So what is my cost? It's the cost of using those server hours or purchasing the server hours. Okay. So why don't I actually this time model it as a maximization problem? So these are going to be my cost of using or purchasing the hours, and numbers 200, 400, and 520 are actually coming from the previous slides. Okay. But then also, I want to maximize my profit. What that means is to take the revenues by completing the tasks. It's going to be X, not X, Y1, 4,000 Y2, and 1,000 Y3. That's my optimization problem. Does that make sense? Now, if you follow this, you might have noticed that there's a reason why I make my X X and Y Y. Right? So X is the number of hours that I commit, right, with different servers. Y is the number of tasks to complete. Okay? And by the way, this is the full formulation. Okay, but I want to actually write with you. And you might actually notice that I write it as less than or equal to constraints instead of equal to constraints. But if you think about it, they are the same. Okay? Because you're going to be minimizing cost anyways. So the optimal solution is going to be eventually the same. But anyways, right? So there's going to be a plot twist. What is it? Well, that was the problem that you thought to solve. But it turns out that the government's regulation on the maximum number of tasks to complete is going to be announced later. Okay? The max number of tasks allowed may change, and these parameters are uncertain. So what parameters are uncertain? Well, these parameters are going to be uncertain. Okay? So what's the story here? You'll have to purchase servers today, right? Today. And in June, there's going to be some regulation, or like next week, there's going to be some regulation announced by the government. But whatever you have purchased, you cannot return them. You live with them. But still, with those resources that you have already purchased, you'll have to make Y decision. With the resources that I've already purchased, how many tasks to complete to make the best out of it, right? So if things were certain, well, basically the uncertain scenario, right? There are three uncertain scenarios when the upper bound, the limits are low, medium, or high. So we categorize them into three different scenarios like this. When low, the upper bound for project one, the number of tasks for project one is going to be bounded above by 50, 20, and 200 for the other two projects. High is going to be, well, higher numbers. And each scenario will have an associate probability, 30%, 40%, and 30%. Okay? So if for some reason you knew exactly what the government is going to announce, then you can simply just replace whatever the upper bounds were with the lower numbers, for example. If you for some reason have perfect information and you know exactly what the numbers should be, and it turned out to be the lower numbers, all you need to do is just replace these numbers for the y constraints, and you solve this problem, and the solution is going to be like this. Right? Your x solution is, well, the number of hours to purchase, y is the number of tasks to complete, and there's 0 for y3. What that means is you're gonna never contribute any of your resources to project 3. And if you think about it, that's kind of obvious, right? Because not obvious really, but it's kind of understandable, plausible in the sense that, well, the revenue is very low for completing one task of project 3. Okay? That's the story. So if you knew the numbers, the solution's kind of obvious. If you knew the numbers and the numbers turn out to be the medium numbers, whatever's in between, well, again, you solve this again, and the optimal solution is going to be this, where again, y3 is 0. Okay? If you knew and these numbers turn out to be high numbers, you do exactly the same. You just replace the red numbers by 250, 250, and 500, and you solve this problem. And again, you purchase this amount of server hours and test this number of tests for different projects. Does that make sense? So this is when you have perfect information. This is what you do. Now, a reality is that, well, server hours need to be purchased before the true upper bound for y is announced. So what do? We'll have to take the stochastic programming modeling approach. Okay? So how should view this problem? You're going to be maximizing the profit where what? Cost of server hours is fixed, but the revenue is going to be the expected value of the revenue, right? Over different possibilities for what this upper bound parameters can be. Okay, so the y variable is our recourse section, right? Something that can adapt to whatever the upper bound parameters turn out to be. Okay, so how should we model this? The reason why I try to cover this example is I'd like you to think about this kind of formulation to, where is it? This format. How would you write this problem in this format? What I'd like you to notice is that, well, all the parameters are uncertain parameters like Q, T, and H are parameterized by omega. Okay? But also Y, the second stage decision itself is also parameterized by omega. So what that means is, well, we will have to introduce duplicates of your Y decisions. Okay? How many duplicates? As many as there are scenarios. We have 3 scenarios: higher upper bound, medium upper bound, and low upper bound. So there's gotta be Y for higher scenario, Y for the medium scenario, and Y for the lower parameter scenario. That's it. Okay, so there are 3 Ys. Oops, spoiler. Huh. So there are 3 Ys, right? Y for project 1, 2, and 3. All I want to do is just to introduce duplicates of Y1, 2, and 3 by maybe adding superscript like H, M for medium, and low. This is it. So the idea is super simple. Okay? And these different duplicates of y's are going to be multiplied by different parameters or affected by different parameters in the constraints. Okay? And the resulting formulation looks like this. Okay? So all I have is not too much different from the original formulation, but it's just that I have a bunch of duplicate constraints to capture three different scenarios, right? And why? I first started with 3y's and now I have like 3 times 3y's. Okay, in the objective function, I have some additional terms to capture the uncertainty, but I have 3 different terms for revenue, right? Each of which is multiplied by the corresponding probability, like this. Does that make sense? So this is basically what is written in a compact format can actually be written in this kind of extensive format for this specific problem. That makes sense. And what I'd like you to notice is also that x is x. I do not introduce duplicates for x. Why? Because x is not subject to uncertainty. X, once you decide on it, like x, you stick with it. Okay? Now, if you solve this problem, what happens? The solution looks like this. And can you make sense of the solution? So what that means is X, you purchase these many hours of servers for server A, B, and C. And Y, there are 3 Ys. Y H star is the Y solution that you implement when the upper bound parameters actually turn out to be high. Okay? In which case, you discard the other Ys. It is the one that you implement. If the numbers turn out to be the medium numbers, you discarded the other 2 Ys and you implement these guys. And what's interesting here is that it is the first solution ever that you see that Y3 is actually non-zero. Does that make sense? What does that mean? This actually captures the nature or the role of your recourse action. You already purchased your server hours, and something happens, and something terrible happens, right? The government's lower bound is terrible, so that, I cannot really do whatever I wanted to do or was planning to do. But then the only thing that I can do is just to do something for project 3, which I would have actually never chosen if I knew these values in advance. Okay? So, well, there's a big difference between the deterministic and stochastic versions of kind of seeing and modeling these problems. Any questions? Okay. Oops. And I was told that the time is wrong in there. Okay. And did it start at 11? Yes, yes. Okay. Any questions? Okay. Okay, so that's the general formulation, really. Okay, now you can have a more practical understanding of how this formulation works. And what I want to emphasize is, well, this formulation looks very simple and elegant, right? Simple. But what it actually looks like in reality is this messy. Okay, so you got to do something about this. We're only looking at 3 uncertain parameters and 3 variables, and already this problem is becoming crazy. What if you have millions of variables and thousands of scenarios? Right? There's no way that you can naively formulate this problem like this and try to solve it using Groby. It's not going to work, of course. Okay? So what do? We'll try to view this problem from a bit of a different angle and try to develop some algorithms. What you want to do is just to abstract away whatever is complicating this formulation, which is for example, the second term of the objective function that is subject to uncertainty. So what I want to do is to define this Q function, right? First, parameterized by both x and not omega, but psi. And that's whenever this term shows up, subject to whatever constraint that is subject to uncertainty. Then you can even further define Q of x, which is simply the expected value of such a Q function over different scenarios. That makes sense? Then now what I am doing is, well, rewriting this as this. It looks super simple. Okay? I'm hiding something. so that it looks super simple, but whatever's happening in that Q function is crazy. But I don't want you to think about this for now, right? Then what I can do is to analyze the structure of the Q function to see if I can do something smart, right? To deal with this almost separately, right? It's not going to be entirely separate, but there's going to be hopefully some kind of decomposition-like approaches to that Q part of this problem. Okay? Now, we call this problem the deterministic equivalent problem, or DEP, because it looks as if the problem is deterministic, but actually it's not. Okay? Okay, it's a deterministic problem in disguise of stochastic program. Okay, so takeaways from the crazy formulation, the extensive form. Good news is that we wrote, right, with all the duplicates constraints and duplicate variables. It's an LP. So, well, theoretically, it's supposed to be easy, but so size can be easily very burdensome, overwhelming, right? So what I'm going to do is to exploit or write the DEP of that problem and try to understand and analyze and exploit the structure of that Q part of the problem to think about algorithms. That's the idea, right? And well, when you try to exploit structure of Q function, there's something good. There should be something good about Q that we can really exploit, right? So what makes Q good? Well, if Q is convex, right, there's a hope. Okay? If P is piecewise linear and convex, it's also good. And piecewise linear and convex, what I mean is like P, well, the Q, the value function, if this is Q of X, roughly speaking, it looks like this. Okay? Right? Separable, well, this is an ideal scenario where the Q is entirely separable over different scenarios. Okay? Too good to be true. But anyways, all these properties of Q will make the problem kind of amenable to efficient algorithm, and that's the goal. So when your problem is an LP, both X and Y are continuous variables in the problem's LP, your Q function will look like this, very roughly speaking. Okay? So very good news. What I'm going to do is to see if I can develop some algorithm to do this. And there's a very nice algorithm that people have developed that looks pretty much like a Newton's method. What is the Newton's method? You start with some solution, you evaluate a subgradient or gradient of that function, and you evaluate the function to update your x, right? And you go over multiple iterations while updating such y's to reach some solution that you think is reasonably good. That's the idea of Newton's method, roughly speaking, right? So what do I do here? I decouple that q of x function from the problem. So what I can do is, well, let's say I'm a person who deals with the q function and you are the guy who's looking at the big picture, like the entire problem. What you can do is you give me an x. I'm going to evaluate my q, right? And my first x, or the first x that you give, suppose it's here, then what I can do is, it is hard to solve or optimize that function, but it's easy to evaluate that function with a given x. Okay, so what I can do is I'm going to take the subgradient of that q function, and it'll, let's say, look like this. Okay, so, well, this piecewise linear function is the original structure of the q function, but suppose that we don't know the exact shape of this function yet. Okay, we don't know this yet, right? What I'm going to do is I'm going to construct an approximation of that function. An approximation, I'm going to do it like in a lower approximation of that function. Okay, so if you give me y x1, then although I didn't know the entire structure of this q, I can actually evaluate it drawing a subgradient that looks like this. And if I optimize my approximation of q based on this subgradient, my next x is going to be this, x2. And with that x2, I can reevaluate that function. And the gradient or subgradient of the function is going to be like this. Okay? And then you update the approximation of your Q function using the first subgradient and the second subgradient. I only have two pieces, right, to build a lower approximation of that Q function. And you optimize that approximation consisting only with the two subgradients, which will give me x3. And then I update it by adding another line like this. Okay. So I've just added my third cut to my approximation. And you can see that the shape of my approximation is kind of converging towards the exact shape of the Q function. Okay, that's what I do. And then let's say I'm tired, right? And I decided to just stop here. And this is my X hat. That's my solution based off of this approximation, right? Now, if you knew the exact shape of this Q function, what would be the optimal solution? The optimal solution is going to be, oops, here. And where did it go? Oh yeah. This is going to be the actual optimized Q value. But what I have is here, Q of X hat. So this is the gap that I have. That's the performance of my approximation. And that's it, right? You've added 3 cuts to define or approximate the Q function. And you can see there are only so many pieces that you'll have to consider. So eventually, this algorithm will actually converge to a solution that matches, that is identical to the optimal solution, the true optimal solution of this problem. Does it make sense? Now, roughly speaking, this is how the algorithm is supposed to be working for solving for that Q function. And this is more exactly what I did here. So Q of X, well, what kind of problem you started with? You started with minimizing C transpose X and Q of X. X is in some feasible region. And Q of X, you started with nothing, right? But then iteratively, you can add this cut and this cut and this cut, the 3 cuts based off of this subgradients of the Q function, evaluated at 3 x's. Okay? So all you need to do is just add these constraints to this problem to slowly converge to an optimal solution to this stochastic program. That's roughly speaking how it works. And this kind of technique, we call it cut generation technique. Okay? So suppose, well, we do this theoretically, then we have L subgradients of X evaluated by L different X's. Then we have updated this problem where instead of writing the second term of the objective function as Q, I can write it as theta. And the theta itself is going to be bounded below by L cuts or at L right-hand side. Right, based off of the subgradients of this Q function, that's it. Any questions? Okay. Okay. So that's the good news, right? There's a technique that I can use to add cuts iteratively. And the way you add cut, you are supposed to be solving one optimization per cut, but hopefully it's not too bad, right? So you can use a constraint generation or cut generation method to approximate a large 2SSP. Now, even better is the very special structure of the constraints of this problem. Okay? So initially, you had this. But then X is X, that is fixed. Not fixed, but it's just a single variable. all you need to do is just to introduce duplicates of this constraints where it is only y and only this part that vary depending on scenarios. So what that means is you can view the structure of the extensive form of the stochastic program like this. Okay? And this is actually more red on my iPad. It looks toned down there. But this is the red part. This is the blue part. What I'm trying to say is, well, this structure allows you to just take an x, right? If you give me some x, let's say x1, then I'm gonna fix everything here. Then all of a sudden, the y problem is decoupled, completely decomposable into how many problems? As many as there are scenarios, like k problems. Okay? It's a nice structure that this problem has, right? Only some feasible y is, once some feasible y is given, the y problems are solved separately, so decomposable. So you might have heard of the Bender's decomposition method. So that's basically what is used for solving this type of two-stage stochastic program, right? So the idea, first, find some good x, evaluate the corresponding y, because all the problems are decomposable. So you can do this separately and generate additional constraints. Okay, so what I can do is each separable problem can evaluate the given x separately, and it can contribute almost separately by adding their own cuts, right? Sending their cuts to the x problem. Okay, and you repeat this process. That's gonna be it. Okay. And the problem that deals with x with approximate q, we call it the master problem. All these y problems that are solved separately, you call them subproblems. Okay? So solve the master problem only in terms of x. And oftentimes you'll have to add some feasibility cuts. What do I mean by feasibility cuts? What if you give x and I tested at x, turns out that with that x, there's no feasible solution for y. There's something wrong with your x. So I send you some cuts. Hey, your x is wrong. Why? Because there's nothing that I can do with y. So I'm gonna just add this cut to make sure that your x is actually feasible for the entire problem. And then you solve the y problem to add optimality cuts. There are two different types of cuts. And it is the optimality cuts that I described using the Q function, the subgradients, right? And you repeat this process. Now, what I'm gonna show you, well, I don't expect you follow everything, but I'm just showing you the exact structure, well, basically how the algorithm actually works. And we call it the L-shaped method. Why is it called the L-shaped method? Because the structure looks like the L-shape, right? But anyways, right, it just adopts the Bender's decomposition idea, basically. You start with some x, and there's going to be two different types of cuts. The cuts with D is the feasibility cuts. The cuts with E are the optimality cuts. Whatever you do, you start with the master problem. You treat that the theta does not exist at first, right? Because you know nothing about theta. Okay? You solve this problem only in terms of x with no cuts. And there's going to be some x. You send it to step 2, where you evaluate the possible feasibility of that x. And if not, well, you add a feasibility cut. And how do I know? Well, you solve this problem. And if you look carefully at this problem, it is not really much than just evaluating whether you can actually, given that x, find a y. And all you need to do is to check this stopping criterion, or check the criterion. Okay? Your objective function value of this problem will indicate whether that x will allow a feasible y or not. Okay? And that's the feasibility cut part. The optimality cut part, well, you solve this problem. Okay? Given x is fixed, you only solve this problem in terms of y, and you evaluate y based on this. And this is the criterion, right, that you use to see whether the x that is given is actually optimal. or it's not, and then hence you'll have to add some optimality cuts. And if you think about it, if you look at the structure of this E, the big E and small e carefully, well, all I am doing here is to assess the reduced cost. And if you remember the LP theory, if you remember how the reduced cost works, well, you check the signs of the reduced cost, and depending on whether you're optimizing or minimizing or maximizing, you want the reduced cost to have like specific signs, right, to declare optimality, right? So what I'm saying is you check this, and that'll indicate where your X is actually optimal or not. If not, you're adding these cuts to guide the master problem to do better. That's it. Okay? Does it make sense? Okay. Now, that was two-stage stochastic program. Already quite involving and challenging. Okay? But many problems that we face in real life, well, it doesn't stop at with two stages, right? It typically involves multiple stages. What that means is you'll have to do something more complicated for that Q, right? We're going to do exactly the same by incorporating everything, like stuffing everything into that Q function, okay? But what is inside that Q is going to be nested, okay? It's going to be nested like this, where, well, we're going to be talking about MSSP, multi-stage stochastic programming, where T is the total number of stages, okay? If T is 2, well, it's just two stages, the same problem that we dealt with. So, well, in this case, instead of Y, I'm going to call it X2. Okay, X2 is going to be my second stage decision. Everything is the same. It's just that Y is replaced with X. Now, what if T is 3? Well, I'm going to have this expectation for the second stage, but if you look at what is inside of the expectation for the second stage, there's going to be expectation for the third stage, and et cetera, et cetera. It's going to be crazy. So this is the full-fledged multi-stage stochastic program where things are going to be nested like this. Okay, well, what that means is you will also have very many constraints if you were to write this problem as in an extensive format. Okay, so thankfully there's this nested decomposition method, albeit computation is still very challenging and messy and nasty. Okay, so how it works? Basically, one way to view multi-stage problem is from like through the lens of dynamic programming, of course, right? You start with the final Q function at the final stage, and you look at the structure, and you look at the middle stage Q function. At the end of the day, you'll be looking at the single Q function that encapsulates everything. Now, one way to do it, as I mentioned, is the nested Bender's decomposition method, or nested L-shaped decomposition method, or NLDS, right? So I'm skipping a bit fast because the general idea is the same, right? But it's a bit convoluted in the sense that if we had only two stages, the master sending me X, and I send to the master the cuts. What if I am in between? What if I am solving this problem for stage 3? Then what I have to deal with is like the problem for stage 2, right? And also a problem for stage 4. Problem from stage 2 will be, giving me X, okay? And I'm supposed to be sending some cuts to the upper stages, of course, but also do the same, the reverse roles for the later stage problems as well, right? And that's what I mean. So I am looking at this stage T, but I'm supposed to be solving like similar cut problems to generate cuts and sending cuts to the prior stage. But also, depending on my result, if I like the X that has been handed down all the way to me from upper stages or earlier stages, if I like it, then I can also send it to my later stage problems. Okay, so I'm not gonna cover this, but there's gonna complicate rules to decide whether you want to send cuts in, whether we're gonna just hand down to later stage my X. That's basically, roughly speaking, how things work. Does it make sense? Okay. Okay, now what we talked about is perhaps the easiest possible version of stochastic program. Now, two-stage stochastic mixed integer program, well, how do you solve it? Well, we cannot use this kind of nice structure of the queue using which we develop the L-shaped algorithm. That's not going to work, right? It's typically very challenging, right? It's a research area that is very active and people are developing various algorithms, but basically the the easiest way of thinking about this problem is like, branch and cut type of algorithm, right? We're supposed to be solving the master problem using branch and bound, and at each node, you're going to be sending cuts, right? The problem. Think about it. Okay, so modeling issues in stochastic programming. So this is how we develop algorithms, but I like you to also think about modeling issues. Do you like the philosophy of stochastic programming, two-stage stochastic programming? And if you're not, if you don't like it, then why, right? What's the idea of stochastic programming? You're optimizing the average of your objective function over uncertainty, right? Have you heard about the flaw of the average? Right? Your average looks good, but what if the underlying distribution has a very heavy tail? Okay? Then is your average still relevant for your problem, right? Are you happy with maybe just like 0.5% of like having some kind of disastrous result, right? If you're not that kind of person, then maybe stochastic program is not the right choice. Okay? So if some applications, you might want a solution that remains safe under any possible realization of the data, right? I'm not a kind of risk neutral person that is happy with the average solution, but I'm a very risk averse person. I want to make sure that whatever happens to the world, my solution is still reasonably good, right? Then you'll have to switch to something different. Okay, not stochastic program. In general, stochastic programming is a good choice if the underlying distributions are given. That's what I mean by data are of stochastic nature. You can point out a very specific probability distributions and you know how to solve these problems. Stochastic programming problems are easily very computationally complex. Okay, so if you can do it, well, deal with it, but oftentimes very hard. Okay, computational tractability is a rare commodity. So the versions that I talked about is, well, it assumes exogenous uncertainty, the farmer's problem, the project management problem, okay? The government is my external environment, no control, right? What if my uncertainty is actually endogenous? The problem will become even complex, okay? And what if, well, I told you like two-stage stochastic integer program is hard, but what if like multi-stage stochastic integer program? Very hard, okay? So that brings us to robust optimization. I realize that I spent a bit too much time on stochastic programming. I'll try to be as efficient as possible. So robust optimization is an alternative to stochastic programming, right? Not because you can just replace stochastic programming with robust optimization, not that sense of kind of alternative. But if your philosophy, if your perspective on that problem is different, right? You don't like the fact that you're averaging out the objective function, then robust optimization is probably the right choice for risk-averse people. A lot of attention has been given to this topic in the last 2 decades and perhaps 3 decades, generally considered like philosophical alternative to stochastic programming, in the sense that you want a solution that is immunized against all realization of the data. The weather, is it going to be hot, moderate, cold? It doesn't matter. I want a solution that just works well. Okay. What's good? Well, there's no stochastic nature that you have to think about this problem. And what is even better is that the most reformulations are known to be tractable. Okay. So modeling choice, be it stochastic programming or robust optimization, it really depends on the context and also you as a modeler, your risk attitude. If you're building a bridge, right? If you're doing something that can actually lead to some disastrous outcome, then maybe averaging is not a good choice. Something like this. Robust optimization in finance, you can determine a portfolio of assets that is robust against all possible realizations. Healthcare, when I try to place these AED devices, I want to just, like save lives by just counting the average lives. Maybe I want to just do the worst case optimization, right? Evacuation routing, we're talking about disasters. So it's better to be a bit risk averse. Okay? So the worst case oriented philosophy, it is appropriate for problems involving low probability, high impact, like building bridges and stuff. But also, one of the criticisms about robust optimization is that because you're trying to cover or be ready for all possibilities, your solution is going to be very conservative, right? So simple illustration, let's say you're looking at maybe 3 constraints, and this is your feasible region, okay? And this is the feasible region that you thought should be when you didn't know about any uncertainty. And what can happen is, well, it turns out that the blue constraint could actually be like this, can actually be like this. Okay? Your green constraint could actually be like this and be like this. And your red constraint can actually be like this. Okay? So with this kind of uncertainty, your feasible region is uncertain, right? What did you do if you were to find a solution that works just well for all possibilities of these constraints? Well, your feasible region just becomes the intersection of all the possible realization of the constraints. So it is much smaller than the original feasible region in this sense. And that's what I mean by being very conservative. Now, you're optimizing over that feasible region, not the average feasible region or the original feasible region. And we call that kind of feasible region the robust feasible region of this problem. Okay? Okay. Make sure that I'm not missing anything. Okay. So that's the geometric interpretation of what robust optimization does. Now, let's focus on the following form of NLP where you minimize C transpose X subject to AX less than or equal to B. If you solve this problem as is, the solution, the resulting optimal solution is going to be called a nominal solution. And suppose for now that only parameters in this A matrix are uncertain. Okay? Anything else is given and certain. There is some coefficients in that A parameters, A matrix that are uncertain. What I can do is to introduce or define an uncertainty set for that A parameters. Okay? And the way that I can introduce my uncertainty set is like this. U is my uncertainty set. That is the set of all the possible A variables, or A matrices. Sorry, not variables, but matrices. Like M by N, the A matrices. I know this matrix is uncertain, but how is it uncertain? Right? The way, like one way that I can define uncertainty around that A is to think about this, right? A naught is going to be the nominal A, which you thought to be. But then A can deviate from that A naught by something like this. This is like the way like to define how A is uncertain. The way A is uncertain is that there's nominal A naught, right? And there are other A's like A1, A2 through AL. You can treat them as some kind of basis, right? Directions in which A, the nominal A can vary. And psi 1, psi 2 is basically the magnitude, right? Of the direction, roughly speaking. So this way, if you define uncertainty of A this way, you can also define your uncertainty entirely in terms of your psi, right? If you know what this Z set is, right? Z is set of all the possible size. If you can characterize that the Z set, you can characterize the entire uncertainty set for the A. Okay? Does that make sense? Okay, that's it. Now, with this construction or structure of uncertainty set for A, what I can do is to define an uncertain linear program or LP subscript U that is basically like this, right? There's this linear problem, but then you're looking at all the different LPs that are parameterized by different A variables, or did I say A variables? A parameters that are from that uncertainty set you just defined. So you can think if the uncertainty set U is a continuous set, then you're looking at a collection of infinitely many LPs here, right? This guy is uncertain. So how do we solve this problem is a challenge. Okay, how do we deal with a collection of infinitely many optimal linear programs, right? And the goal of the robust optimization technique is, or the framework is to find a solution that is immunized to whatever A that actually turns out to be, well, your solution is guaranteed to have some objective value. That's it. Okay, so let me cover a bit more and try to move on to the next lecture. So if your A is uncertain as a whole, then you can define it like this. If your A matrix is uncertain in constraint-wise or row-wise, you can define separate uncertainty sets for different rows of the constraints. But really, the way you solve this problem is going to be exactly the same, right? So the challenge is then, well, how do we define that uncertainty set U, right? What should be that uncertainty set U that has all the possible realization of A? That's the challenge, right? So without loss of generality, we're going to be assuming that the objective function is certain and the RHS is certain, and there's only single uncertain constraint. So we're looking at this problem. Okay, and it is that A constraint vector that is uncertain in the uncertainty set like this. Now, your A vector is uncertain in the sense that it is a deviation of the nominal vector A naught, and deviation is governed by the psi parameters. And then you can reformulate this uncertain constraint into this, right? Where your B is really nothing more than just a matrix that has like A columns, A1, A2, AL, okay? And you can move everything over to where the left-hand side of this equality, then you can express the uncertain constraint like this. Okay? And it is this form that I'd like to focus on when I talk about robust optimization. So what I really mean by this is, well, this version of uncertain constraint, I express uncertainty in terms of the uncertainty set U, but in this format, I can characterize my uncertainty set really purely depending on what my psi is, and psi is going to be in Z. So whenever I try to define an uncertainty set, all I need to do is to define what is my Z. Okay, what is my Z? That's how I characterize the uncertainty set. Okay, so basically, we're looking at a constraint that is uncertain. And how it is uncertain is that it is only the A vector, the constraint vector that is uncertain. Okay, and how it is uncertain is basically defined by a nominal vector A not deviated by other basis vectors A1 and AL multiplied by its each of its their magnitudes, psi 1 and psi 2 through psi L. If I reformulate that, and the constraint will look like this, where the difference is that, well, instead of defining the uncertainty set U as a set of A's, I can define the uncertainty set as Z, which is the set of size, right? The way the nominal vector can be deviated is dictated by psi vectors, right? And I am defining an uncertainty set Z, which is set of all the possible size. Okay? Now, the problem really then amounts to how do we define that Z, the uncertainty set, right? The set of possible size. Well, there are different types of uncertainty sets. Probably the most well-known and the easiest uncertainty sets are the following two, which is the box uncertainty set and the ball uncertainty set. The box uncertainty set is, well, the psi parameters, right, is going to be constrained in the sense that max norm or infinity norm of psi is going to be bounded above by some radius rho. Okay, so what is this max norm? Max norm is the infinity norm. It's just it picks the maximum absolute value across all the components of an underlying vector psi. Okay, whereas the ball uncertainty set, it is the set of psi such that the two norm, right, of psi is gonna be within some radius rho. Okay, this is how you define uncertainty set. Can you visualize this, right? So let's say given the same radius, if you look at the box uncertainty set and the ball uncertainty set with the same radius, which uncertainty set is more conservative? Can you imagine? Psi, again, psi. Psi has like L components, right? Each component of psi is the impact of deviation vector A1, A2 through AL, right? So the bigger the psi is, the more uncertain your parameter is. That's one way to think about this, right? So given the same rho, the radius, rho, box versus ball, which one is more conservative? The box is more conservative because of that geometry, right? So box intercept is highlighted in red, which is actually drawn here as that red box, whereas ball intercept highlighted in blue color is the circle inside of it, right? So the box is bigger than the circle. What does that mean? The box captures more size, including the size that are already included in the ball. So what that means is if you take the ball box uncertainty set, you are treating your uncertainty more conservatively. That's the intuition. Okay? Now, if you focus on the box and the ball uncertainty, you can really think of them as norm-based uncertainty. And there's a theory that says that, well, if you define your z vector as a box uncertainty set that looks like this, then you can basically reformulate that uncertain constraint as follows. Okay? So why is this? What's with that reformulation? Any idea? So you started from that uncertain constraint and you reformulated that as that. Why is this good? Because there's no more random variable. Okay? Rho, the radius is given. B is simply just a matrix that consists of L column vectors, right? The deviation vectors. And that's it, right? So all of a sudden, you eliminated that random part of the constraint and you rewrote that as the following deterministic constraint. Now, what's the interpretation? Now, if you think about it, A naught is the nominal vector, right? Which you thought should be true, turns out not true. Okay. So this is a nominal constraint. What you have is something in between, right? So what that means is you're giving some room between the left-hand side and right-hand side to be more conservative. The bigger this part is, the more conservative. The smaller this part is, the less conservative that you become in terms of this uncertain constraint. That's the interpretation, right? For some reason, I cannot really make the volume. It just keeps going up like this. I don't know why. Anyways, okay? Now that's how you reformulate the box uncertainty based on certain constraint. If this is a ball, then you reformulate that as follows. Okay, where what is in between the red part, the margin between left and right hand side is based on the 2 norm of B transpose X. That's it. Okay? So that's the reformulation for the 2 norm. Now, what I'd like you to notice is that when the uncertainty set was defined based on infinity norm, what the norm that shows up in the constraint is 1. When the norm defined in the uncertainty set is 2, then what shows up in the reformulation is 2. There's something going on here, right? And if you generalize this reformulation idea, if you define the uncertainty in terms of P norm, what happens is that what shows up in your reformulation, that margin term, will be D norm term, where D is basically the dual norm of P. So what's the dual norm? Well, we say D norm is the dual norm of P if this is true, right? And if you can just plug in that infinity and 1 into that equation, 2 and 2 into that equation, well, it holds. Okay, so the takeaway is that if you define your uncertainty set using norms with a given radius, rho, then you can always reformulate it as the following general term using the idea of dual norm. Right? So not only is RO robust optimization useful for immunizing your solutions across all uncertain scenarios, it is also computationally tractable. It all of a sudden becomes something tractable. Well, you can reformulate this as linear constraints. This is a second order cone program, basically, right? And depending on what your D is, you can also convexify this problem, or it is already convex, actually. Okay? So that's the idea. So I'm going to just give you a very quick example, which is a portfolio optimization problem. Okay? Suppose there are 200 assets, right? Indexed by L from 1 through 200. And the last one, indexed by 200, is the money in the bank, meaning it is guaranteed to give you 5% of rate of return. Okay? No uncertainty. And now the remaining assets from indexed by 1 through 199, their rate of return is uncertain in the sense that they follow some mean, but they follow a uniform distribution in the sense that the lowest possible is mean minus sigma, and the highest possible is mean plus sigma. Okay? And the formulas for UL and sigma L are the following. So what that means is UL, when L is 1, right? U1, the mean is going to be the highest, right? Because all you need to do is just plug 1 here, right? And the L, it will increase like from 1 to 2 to 3, all the way through 199. So mu changes, and also sigma changes. So what I'm trying to set up here is that there are some assets that have like higher means, but also higher sigmas. Those that have lower means will have lower sigmas. What that means is higher returns involve higher risk, lower returns involve lower risk. And eventually, the last one is the one that gives you the lowest return with no risk. Okay? And I can formulate this problem as follows, where I try to maximize the rate of return, the total rate of return across the 200 assets. And the sum is gonna be 100. So what that means is suppose that you have $100 to invest across these assets, or you can even think of it as like 100% of your money. Okay, so what do? We can reformulate this problem in different versions of robust optimism problems using like the ball uncertainty set, the box uncertainty set. We're gonna see what happens to different versions of robust optimization models. Okay, so I'm gonna skip the derivation. But basically, this is what happens when the uncertainty is ignored. When there's no uncertainty, what you do is put all the money into the highest return asset because you're ignoring that highest risk that follows it, right? So obviously, the optimal solution is all in for the first one, 0, which is my asset 1. Whereas if I use the box uncertainty set, interestingly, box uncertainty set, I said it's supposed to be very conservative. Okay. What happens is, well, your optimal solution turns out to be invest everything into asset 200, which is like no risk, but lowest return. What happens if you use the ball uncertain set? It looks like this, where you are kind of reasonably aggressive, somewhat, but you try to diversify your portfolio this way so that you gradually decrease your investment through some less risky investments. So this is basically how robust optimization understands your problem, right? And also depending on what type of uncertain set that you use, right, your solution may differ. So it really depends on your risk attitude at the end of the day. And now if you compare this, then, well, you're really diversifying when it comes, when you actually use the ball uncertain set. Okay. And this is consistent with the rule that everyone's saying, right? For risk aversion, you gotta diversify. Okay, and then I actually simulated these three different solutions to see what the actual like distributions of the achieved total rate of returns. When you use the box uncertainty set, of course, there's no risk, so guaranteed 5% rate of return. Whereas if you use the deterministic approach, then you can basically have your return that is as low as this, but as high as this. Okay? And the ball uncertain set, I think this is my favorite, right? It will always be better than that red dashed line, which is the box uncertainty solution. And the variance is very small. So you're guaranteed to be within this range of, um, well, results as a result of implementing the ball uncertainty set-based solution, right? Robust optimization. Now, can we be more flexible, right? We talked about the box uncertainty set, ball uncertainty set. These are a bit too basic, right? So what I can do is maybe I can be a bit more flexible by defining an uncertainty set that looks like this, and we call it the polyhedral uncertainty set, where my psi is a set, right? Well, my z is the set of psis that satisfy these polyhedral constraints. Okay, this is more flexible. Now, for such a polyhedral uncertainty set, there's a way to reformulate it as, I mean, into not flexible, a computationally tractable formulation. Basically, you take exactly the same format, but psi is subject to these polyhedral constraints. You reformulate it as follows. Okay? Then what you have is there's this max or maximization problem inside that uncertain constraint. Right? If you take a step back, you're basically looking at this problem. You're minimizing C transpose X subject to AX plus something, right? And that something itself inside is maximization problem. Okay? And this is a tricky problem. It's a min-max problem. Okay? So I'm intentionally also writing that max part in Q, right? In trying to also do something about this Q to make it look better computationally. Okay? And the reason why it's max is because we're going to take the worst psi over this polyhedral constraints of psi. Okay? So what did you do? It's a min-max problem. It's challenging. But this part, the Q, is a maximization problem itself. What did you do? Any idea? Min-max problem's bad. But maybe if there's a way to make it like a min-min problem, maybe that's better because the objectives are aligned. Any idea? How do you make your max problem a min problem? You, apply negative sign. That might work, but there's a bit fancier way of doing it, which is to take the dual of it, right? If you take the dual of the minimized problem, the dual problem is a min problem, okay? So what you do, take that maximizing problem for Q, you dualize it, then the dual looks like this. And now your problem all of a sudden looks like this, where your constraint is AX plus QX where Q of X part is a minimization problem, your objective function is also a minimization problem. So what can happen is you can merge this part into whatever the K is. So it'll look like this. Okay? And if you solve the latter problem written in blue and find an optimal solution, right? Whatever y that is from that solution will also satisfy this problem because of the mean nature of the Q problem. Okay? So this is how you reformulated the polyhedral uncertainty set-based robust optimal problem into an equivalent but linear, easy to solve reformulation. That's the takeaway, right? Again, one of the biggest kind of perks of robust optimization is computational tractability. Okay? And of course, there are other types of uncertainty sets, like ellipsoidal is easy to kind of imagine, as in what problem can, well, people can actually generalize the ball or box uncertainty sets. There's some discrete uncertainty set type of interpretation here. Well, you take like discrete number of possibilities and you robustify your solution over them. And there's budget uncertainty set. Budget uncertainty set is basically you're giving a budget, like how many parameters are allowed to be uncertain or how much of these parameters are allowed to be deviating from the nominal parameters, something like this, right? And for each of this variance, there's the corresponding reformulation that is tractable. Now, in the earlier part of lecture 2, you saw two-stage stochastic programming, and you can also do two-stage robust optimization. The story is the same. X is the first stage decision. Y is the second stage decision. Uncertain scenario is going to be realized in between. But instead of minimizing the average of the second stage objective function, I want to robustify it, right? Then it's robust optimization in 2/2 stages, right? Now, this problem is a max mean problem, which is even more challenging. And there's a nice paper published in Operations Research Letters by Dr. Bo Zhang, who some of you post-tech students know very well. I think the paper is worth a read. So I'm not going to talk about too much of detailed derivation of that. So I'm going to move on, right? And a very popular approach that has received a lot of attention recently is distributionally robust optimization. The way I interpret this is, well, basically it's the robust optimization take on stochastic programming. If you think about stochastic programming, you assume that some distributions are known, but what if distributions are not known? Okay, but instead, you observe some data and the data will allow me to establish some kind of empirical distribution, but I am not too confident with that in the sense that maybe, right, there's a set of distributions, right, that can still be relevant. Okay, so instead of defining an uncertainty set for parameters, you're defining an ambiguity set, which is, you can think of it as kind of uncertainty set for distributions, right? The ambiguity set P is the set of distributions that are close to the true distribution in some sense. Okay, and then you're going to find a solution that is robust against all the possible realizations for this distribution. Okay, and you can see this problem as follows. You minimize your objective function by finding x that minimizes the max or sup of the expected value of your objective function, where the expectation is taken over distributions, and the distribution can be anything in that set P. Okay, and that set P is the ambiguity set. It's the set of distributions that you think are close to the true one. So now in DRO, perhaps the most important task is how to define that ambiguity set. Like how we define the uncertainty set in the traditional RO setting. How do we define the ambiguity set? Well, there are many different things, right? For example, there's kind of moment-based ambiguity set where you just collect distributions that have the same mean and variance, one way. What I find very interesting and impactful is the Wasserstein distance-based RO or DRO. What is the Wasserstein distance? It's the distance between two distributions. You can think of it as the effort, the cost of moving mass from one distribution to another. You can think of it as some kind of distance, right? And then what you can do is you analyze your data, you establish an empirical distribution, and then you define a set of distributions that are within a certain given Wasserstein distance from that empirical distribution. Now you're going to find a solution that is robust against all the possible distributions within that Wasserstein distance. Okay? That's that. And again, in some cases, you can derive the equivalent tractable reformulations. So to wrap up, really, we discussed stochastic programming and robust optimization. Now, if you didn't follow some of math, it's okay, because all you need is the different perspectives from RO and stochastic programming. Stochastic programming, it minimizes the average, the expectation of the objective function. And in some cases, RO is better, right? And it is the modeler's role in kind of deciding which modeling technique is more appropriate for a certain application. Okay, and stochastic programming can be very challenging computationally, whereas robust optimization, one of the goals in this area is to really find a tractable reformulation. Okay, now RO, stochastic programming, they seem to be at two extremes, right? If you think of this kind of risk attitude as this kind of spectrum, as P is here, RO is here, and maybe there's something in between, and yes, there is, right? You might have heard of chance constraint or probability or probabilistic constraint programming, which is trying to find a solution that satisfies the uncertain constraint maybe 95% of the time. Something like this. CVAR-based or VAR-based or risk-averse stochastic programming, all very popular and highly flexible modeling approaches.